Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the shadow of the 20th century's dawn, a brilliant mind envisioned a world without power lines. Nikola Tesla, the Serbian-American inventor whose alternating current system still powers our homes today, dreamed of transmitting electricity through the very air we breathe. Standing before his experimental tower in Colorado Springs in 1901, Tesla believed he could harness the Earth's natural electrical charge to send power wirelessly across vast distances. His vision seemed like pure fantasy then, yet today, as humanity grapples with climate change and energy security, scientists are seriously considering beaming power from orbital satellites directly to Earth. Tesla's wireless power transmission experiments in Colorado Springs involved creating artificial lightning bolts that could reach heights of over 130 feet. He theorized that the Earth itself could serve as a conductor, allowing electrical energy to travel through the ground and atmosphere to receivers anywhere on the planet. While his ambitious Wardenclyffe Tower project ultimately failed due to financial constraints, the fundamental physics behind his ideas remain sound. Tesla understood that electromagnetic waves could carry energy, a principle that forms the backbone of modern wireless power transmission research. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The concept of space-based solar power emerged in 1968 when Peter Glaser, an aerospace engineer, proposed collecting sunlight in orbit and beaming it to Earth using microwaves. Unlike Tesla's terrestrial approach, Glaser recognized that space offered unique advantages: constant sunlight without atmospheric interference, no weather disruptions, and the ability to capture solar energy 24 hours a day. His vision involved massive satellites equipped with solar panels that would convert sunlight to electricity, then transform that electricity into microwave beams directed toward receiving stations on Earth. Modern space-based solar power systems would dwarf anything Tesla could have imagined. Current proposals call for satellites with solar panel arrays spanning several square kilometers, capable of generating gigawatts of power. These orbital power stations would orbit at an altitude of approximately 22,300 miles above Earth, in what scientists call geostationary orbit. At this precise distance, satellites complete one orbit every 24 hours, allowing them to remain fixed above a specific location on Earth's surface. The physics of wireless power transmission relies on converting electrical energy into electromagnetic radiation, transmitting that radiation through space or atmosphere, and then converting it back to electrical energy at the receiving end. This process involves sophisticated engineering challenges that Tesla's era couldn't adequately address. Modern systems use precise frequency control, typically operating at 2.45 GHz, the same frequency band allocated for industrial, scientific, and medical applications worldwide. Contemporary researchers have achieved remarkable progress in wireless power transmission efficiency. Laboratory demonstrations have successfully transmitted power over distances of several miles, with conversion efficiencies exceeding 80%. These achievements suggest that Tesla's dream of wireless power transmission wasn't merely visionary thinking but represented a fundamental understanding of electromagnetic principles that technology is finally catching up to implement. The urgency of addressing global energy challenges has renewed interest in space-based solar power. As traditional fossil fuel reserves dwindle and climate change accelerates, the prospect of accessing the virtually unlimited solar energy available in space becomes increasingly attractive. Space-based systems could potentially generate power continuously, unaffected by Earth's day-night cycle, seasonal variations, or weather patterns that limit terrestrial renewable energy sources. The journey from Tesla's experimental tower to modern orbital power stations represents more than technological evolution. It embodies humanity's persistent quest to harness nature's fundamental forces for the betterment of civilization. The fundamental science underlying wireless power transmission rests on James Clerk Maxwell's electromagnetic field equations, formulated in the 1860s. These mathematical relationships describe how electric and magnetic fields propagate through space as electromagnetic waves, carrying energy at the speed of light. When Tesla conducted his experiments, he intuitively grasped these principles, though the theoretical framework was still being developed by physicists worldwide. Electromagnetic waves exist across a vast spectrum, from extremely low frequency, radio waves to high-energy gamma rays. For wireless power transmission, engineers must carefully select frequencies that balance transmission efficiency with safety considerations. The microwave portion of the electromagnetic spectrum, particularly around 2.45 GHz, offers an optimal compromise. This frequency penetrates Earth's atmosphere with minimal absorption, while remaining safe for biological exposure at controlled power levels. The process of wireless power transmission begins with power conversion. Solar panels in space-based systems convert photons directly into electrical current through the photovoltaic effect, discovered by Alexandre Edmond Becquerel in 1839. These panels, constructed from semiconductor materials like silicon or gallium arsenide, can achieve conversion efficiencies exceeding 30% under the intense, unfiltered sunlight available in space. Advanced multi-junction solar cells, incorporating multiple semiconductor layers, have demonstrated efficiencies approaching 50% in laboratory conditions. Converting electrical power to electromagnetic radiation requires sophisticated transmitter systems. Modern designs employ phased array antennas consisting of thousands of individual antenna elements working in precise coordination. Each element transmits a portion of the total power, with careful phase control ensuring that electromagnetic waves combine constructively at the intended target while minimizing power transmission in unwanted directions. This beamforming technology, originally developed for radar applications, allows precise targeting of power beams across vast distances. The receiving system, called a rectenna, combines antenna and rectifier functions to convert incoming microwave energy back to direct current electricity. Rectennas consist of thousands of dipole antennas connected to rectifying diodes, typically using Schottky barrier diodes for their fast switching characteristics and low forward voltage drop. The rectified power then requires conditioning through filters and voltage regulators before integration with terrestrial power grids. Atmospheric effects significantly influence wireless power transmission efficiency. Earth's atmosphere absorbs and scatters electromagnetic radiation through various mechanisms. Water vapor absorption peaks occur at specific frequencies, creating transmission windows where power loss remains minimal. The 2.45 GHz frequency lies within such a window, though atmospheric conditions like rainfall can still cause signal attenuation. Advanced systems incorporate adaptive beamforming to compensate for atmospheric disturbances in real time. Power transmission efficiency depends on multiple factors, including transmitter design, atmospheric conditions, beam spreading, and receiver characteristics. The inverse square law dictates that power density decreases proportionally to the square of distance from the transmitter. However, focused beams can maintain higher power densities over extended distances compared to omnidirectional transmission. Current theoretical models suggest that space-to-Earth wireless power transmission could achieve overall system efficiencies between 40 and 60%. Safety considerations require careful attention to power density limits. Microwave radiation at high intensities can cause heating of biological tissues, similar to microwave oven operation. International safety standards limit continuous exposure to power densities below 10 milliwatts per square centimeter for the general public. Space-based power systems must design beam patterns that remain well below these limits, outside designated receiving areas. Beam steering capabilities allow orbital power stations to track multiple ground-based receivers or redirect power-based, on-demand patterns. Advanced phased array systems can electronically steer beams without mechanical movement, enabling rapid response to changing power requirements. This flexibility represents a significant advantage over terrestrial power generation, where transmission infrastructure limits power distribution options. The precision required for effective wireless power transmission demands sophisticated control systems operating in real time across interplanetary distances, setting the stage for examining the engineering challenges of implementing such systems. Constructing gigawatt-scale power satellites presents engineering challenges that dwarf any previous space-based construction project. These orbital power stations would require solar panel arrays spanning areas equivalent to several square kilometers, with total masses potentially exceeding 10,000 tons. Current heavy-lift rockets like NASA's Space Launch System can deliver approximately 140 tons to low Earth orbit, meaning a single power satellite would require dozens of launches using conventional approaches. The structural design of space-based power systems must withstand the harsh environment of space while maintaining precise alignment for effective power transmission. Solar panels experience thermal cycling between plus 150 degrees Celsius when facing the sun and minus 150 degrees Celsius in Earth's shadow. This extreme temperature variation causes materials to expand and contract repeatedly, creating mechanical stress that can lead to structural fatigue over time. Engineers must select materials and design configurations that maintain structural integrity through thousands of thermal cycles over operational lifetimes, spanning decades. Micrometeorite impacts pose another significant threat to large orbital structures. Space debris, ranging from paint flecks to defunct satellites, travels at velocities up to 17,500 miles per hour in Earth orbit. Even tiny particles carry tremendous kinetic energy capable of damaging solar panels or critical components. Power satellites require robust shielding and redundant system designs to continue operating despite inevitable impact damage. Some proposals incorporate self-healing materials or modular designs, allowing damaged sections to be isolated while maintaining overall system functionality. Station-keeping requirements for geostationary orbit demand continuous propulsion system operation. Gravitational perturbations from the Moon and Sun, along with solar radiation pressure, gradually alter satellite orbits over time. Maintaining precise positioning requires regular thruster firings, consuming propellant that must either be launched from Earth or manufactured in space. Advanced electric propulsion systems using ion drives can minimize propellant requirements, but still represent a significant operational challenge for massive power satellites. Beam pointing accuracy presents perhaps the most demanding technical requirement. Power beams must remain precisely targeted on ground-based receiving stations spanning only a few square kilometers from distances of 22,300 miles. This precision requirement equals hitting a target the size of a dinner plate from a distance of over 100 miles. Achieving such accuracy demands sophisticated attitude control systems using gyroscopes, star trackers, and GPS receivers working in coordination to maintain satellite orientation within fractions of a degree. Power management across the satellites. Electrical systems requires advanced control algorithms coordinating thousands of individual components. Solar panel output varies with orientation and shadowing conditions, while power transmission systems must maintain constant beam characteristics. Energy storage systems using batteries or flywheels provide power during brief eclipse periods when Earth blocks sunlight, though these storage requirements represent additional mass and complexity. Assembly techniques for space-based construction differ fundamentally from terrestrial approaches. Astronauts in spacesuits can perform limited assembly tasks, but constructing kilometer-scale structures requires robotic systems or entirely new construction methodologies. Some proposals suggest manufacturing components directly in space using materials extracted from asteroids or lunar resources, potentially reducing launch costs but introducing additional technological challenges. Communication systems linking ground control stations with orbital power platforms must maintain continuous connectivity despite the satellite's geostationary orbit. Signal delays of approximately 250 milliseconds each way complicate real-time control operations. Autonomous systems capable of responding to emergencies without ground intervention become essential for safe operation. requiring artificial intelligence systems more sophisticated than current space-qualified computers. Maintenance and repair operations in geostationary orbit present unique challenges compared to missions in low Earth orbit, where the International Space Station operates. The high radiation environment and extreme distance from Earth limit human presence, while robotic repair missions require months to reach geostationary altitude. Designing systems for long-term autonomous operation without maintenance becomes crucial for economic viability. Power conditioning and transmission equipment must operate reliably in the space environment for decades without human intervention. Electronic components face constant bombardment from cosmic radiation and charged particles that can cause single-event upsets or gradual degradation over time. Radiation-hardened components typically lag behind commercial technology by several generations, potentially limiting system performance and efficiency. These engineering challenges require revolutionary advances in space technology, but the potential benefits of unlimited clean energy drive continued research and development efforts worldwide. The past decade has witnessed remarkable progress in space-based solar power research, with multiple nations and organizations developing increasingly sophisticated demonstration systems. Japan's space agency, JAXA, achieved a significant milestone in 2015 by successfully transmitting 1.8 kilowatts of power wirelessly over a distance of 55 yards using microwave transmission. This ground-based experiment validated key technologies required for space-based systems, including precise beam targeting and efficient power conversion. China has emerged as a major player in space-based solar power development, announcing ambitious plans to deploy orbital power stations by 2030. The China Academy of Space Technology has constructed ground-based test facilities capable of demonstrating wireless power transmission over distances exceeding 6 miles. Chinese researchers have achieved power transmission efficiencies exceeding 75% in controlled laboratory environments, approaching the theoretical limits for current rectenna technology. The European Space Agency has initiated the Solaris program, a comprehensive study examining the feasibility of space-based solar power for European energy needs. This 3-year research initiative, launched in 2022, brings together aerospace companies, research institutions, and energy utilities to address technical, economic, and regulatory challenges. Preliminary findings suggest that space-based systems could provide competitively priced electricity by 2040, assuming continued technological advancement and cost reductions in space launch services. Private companies have joined government agencies in pursuing space-based power technologies. Space Solar, a British company, has developed innovative lightweight satellite designs using advanced materials and deployable structures. Their proposed satellites would unfold in orbit like origami, dramatically reducing launch volume requirements, while maintaining large power collection areas. Demonstration missions planned for 2025 will test key deployment mechanisms and power transmission technologies in low Earth orbit. Breakthrough advances in photovoltaic technology have significantly improved the economics of space-based solar power. Perovskite solar cells discovered in 2009 offer the potential for lightweight, flexible solar panels with efficiencies exceeding 40%. These materials can be processed at lower temperatures than traditional silicon cells, potentially enabling in-space manufacturing using automated systems. Research teams at multiple universities have demonstrated perovskite cells maintaining efficiency for over 1,000 hours in simulated space conditions. Wireless power transmission efficiency has improved dramatically through advances in metamaterial antenna design. Researchers at Stanford University have developed rectennas incorporating metamaterial structures that can capture electromagnetic energy across broader frequency ranges with higher conversion efficiency. These devices achieve power conversion, efficiencies exceeding 90% at laboratory scales, representing a significant improvement over conventional designs. Robotic assembly technologies crucial for space-based construction have advanced through multiple demonstration programs. NASA's robotic refueling mission has successfully demonstrated automated spacecraft servicing operations in orbit, including fluid transfer and component replacement. Similar technologies could enable autonomous assembly and maintenance of large power satellites without human intervention. The Defense Advanced Research Projects Agency's Phoenix program has tested robotic systems capable of harvesting components from defunct satellites for reuse in new missions. Artificial intelligence systems are revolutionizing space-based power system control and optimization. Machine learning algorithms can predict power demand patterns, optimize beam steering for maximum efficiency, and automatically adjust system parameters to compensate for component degradation or environmental changes. These autonomous control systems reduce dependence on ground-based operators while improving overall system performance and reliability. Advanced materials research has produced lighter, stronger structural components suitable for large space-based systems. Carbon nanotube composites offer strength-to-weight ratios 10 times better than steel, while maintaining excellent electrical conductivity. These materials could enable construction of massive solar arrays and transmission antennas that would be impossible using conventional materials. Several aerospace companies have successfully manufactured small-scale components using these advanced materials for space applications. Power beaming demonstrations have achieved increasingly impressive ranges and power levels. The U.S. Naval Research Laboratory successfully transmitted power between aircraft separated by distances exceeding 1 mile, demonstrating airborne power relay concepts that could extend the range of space-based systems. Ground-to-space power transmission experiments have achieved successful operation across distances exceeding 100 miles, validating atmospheric propagation models used in system design. International collaboration has accelerated technological development through shared research programs and standardization efforts. The International Space Solar Power Society coordinates research activities among member nations, facilitating technology transfer and avoiding duplication of effort. These collaborative programs have established common technical standards for wireless power transmission systems, essential for international deployment of space-based power infrastructure. These technological advances are rapidly approaching the point where space-based solar power transitions from research curiosity to practical energy solution, though significant challenges remain. The economic viability of space-based solar power hinges primarily on launch costs, which have undergone dramatic reductions over the past decade. SpaceX's Falcon Heavy rocket has reduced launch costs to approximately $1,400 per kilogram to low Earth orbit, compared to over $10,000 per kilogram using traditional launch systems. Even greater cost reductions appear possible with developing technologies like SpaceX's Starship, which aims to achieve launch costs below $100 per kilogram through full reusability and economies of scale. Current estimates suggest that a 1 gigawatt space-based solar power satellite would cost between $10 and $20 billion to construct and deploy, including launch expenses, manufacturing costs, and ground-based infrastructure. This represents a significant investment comparable to large terrestrial power projects like nuclear power plants or major hydroelectric facilities. However, unlike terrestrial systems limited by geography and weather, space-based systems can operate continuously at full capacity, potentially generating 5 to 10 times more energy annually than equivalent terrestrial solar installations. Operational costs for space-based power systems remain relatively low once deployed. Unlike fossil fuel plants requiring continuous fuel purchases, space-based systems utilize free solar energy with minimal ongoing expenses. Primary operational costs include ground-based control facilities, maintenance operations, and eventual satellite replacement after 20 to 30 years of service. Insurance costs may initially be significant, given the limited operational history of such systems, but should decrease as technology matures and reliability improves. Manufacturing costs represent a substantial portion of total system expenses, with current estimates suggesting that space-qualified solar panels cost approximately 5 to 10 times more than terrestrial equivalents. However, economies of scale could dramatically reduce these costs as production volumes increase. Mass production techniques developed for terrestrial solar panels, combined with simplified designs optimized for space applications, could potentially achieve cost parity with ground-based systems within 2 decades. The energy market potential for space-based solar power appears enormous, particularly in regions with limited renewable energy resources. Island nations, Arctic communities, and developing countries with inadequate electrical infrastructure represent prime early markets where space-based power could compete favorably with alternatives like diesel generators or long-distance power transmission lines. Japan and South Korea have expressed particular interest in space-based power as alternatives to fossil fuel imports for energy security. Terrestrial renewable energy costs provide important benchmarks for evaluating space-based solar power economics. Wind power currently costs between $30 and $60 per megawatt-hour in favorable locations, while terrestrial solar power achieves costs between $20 and $50 per megawatt-hour. Space-based systems must achieve comparable costs to compete effectively, requiring continued technological advancement and cost reduction in space technologies. Energy storage requirements significantly affect the economic comparison between space-based and terrestrial renewable systems. Ground-based solar and wind power require expensive battery storage or backup generation to provide continuous power, adding substantial costs to overall system economics. Space-based systems provide continuous power without storage requirements, potentially offering economic advantages despite higher initial costs. Carbon pricing mechanisms increasingly favor zero-emission energy sources like space-based solar power. Many countries have implemented carbon taxes or cap-and-trade systems that add costs to fossil fuel generation while providing economic incentives for clean energy alternatives. As carbon prices increase globally, space-based power becomes more economically competitive compared to conventional generation sources. International energy markets could drive rapid adoption of space-based power systems through power purchase agreements and international electricity trading. Countries with abundant launch capabilities could develop space-based systems for export to nations lacking suitable renewable energy resources. Such arrangements could provide stable, long-term revenue streams, supporting initial investment costs. While meeting growing global electricity demand, risk assessment and financing challenges currently limit private investment in space-based solar power development. Traditional energy project financing relies on proven technologies with predictable performance records, while space-based systems represent relatively unproven technology with limited operational history. Development of appropriate insurance. Products and government risk-sharing mechanisms will likely be necessary to attract sufficient private capital for large-scale deployment. Economic modeling suggests that space-based solar power could achieve grid parity with conventional energy sources within 15 to 20 years, assuming continued technological advancement and launch cost reductions. Early systems will likely target premium markets where customers pay higher prices for reliable clean energy, gradually expanding to broader markets as costs decrease and technology matures. The transition from research and development to commercial deployment requires sustained investment and supportive government policies, setting the stage for examining implementation strategies and policy frameworks. Implementing space-based solar power systems requires unprecedented international cooperation and regulatory coordination across multiple domains, including space law, telecommunications, environmental protection, and energy markets. The Outer Space Treaty of 1967 establishes fundamental principles for space activities, but lacks specific provisions addressing large-scale commercial power generation. New international agreements will likely be necessary to establish clear property rights, operational responsibilities, and liability frameworks for space-based energy infrastructure. Frequency allocation presents one of the most immediate regulatory challenges for space-based power transmission systems. The International Telecommunication Union coordinates global radio frequency usage to prevent interference between different applications. Power transmission systems operating at 2.45 GHz must coexist with existing users, including Wi-Fi networks, Bluetooth devices, and industrial heating equipment. Dedicated frequency bands may require allocation specifically for space-based power transmission, necessitating complex international negotiations among ITU member nations. Safety protocols for microwave power transmission must address both occupational exposure for workers and environmental protection for wildlife. Aviation authorities require detailed analysis of power beam effects on aircraft electronics and pilot safety when flight paths intersect transmission corridors. Migratory bird populations could potentially be affected by high-power microwave beams, requiring environmental impact assessments and possibly seasonal transmission restrictions in sensitive ecological areas. Grid integration challenges involve connecting space-based power systems to existing terrestrial electricity networks designed for conventional generation sources. Power grid operators must accommodate the unique characteristics of space-based systems, including constant power output, precise geographic targeting, and potential beam steering capabilities that could redirect power between different grid connection points. Smart grid technologies will be essential for managing these dynamic power sources effectively. Deployment timelines for space-based solar power systems depend heavily on policy decisions regarding government support, regulatory approval processes, and international cooperation agreements. Optimistic projections suggest that first-generation demonstration systems could begin operation by 2030, followed by commercial-scale deployments throughout the 2030s and 2040s. However, these timelines assume continued technological progress and sustained financial support from both government and private sources. Technology transfer policies will influence the global distribution of space-based solar power capabilities. Countries with advanced space technologies face decisions about sharing expertise with international partners versus maintaining competitive advantages in emerging energy markets. Collaborative development approaches could accelerate overall progress while ensuring broader access to space-based power benefits, but may require careful negotiation of intellectual property rights and technology export controls. Environmental. Regulatory frameworks must address the unique aspects of space-based power systems, including space debris generation, electromagnetic emissions, and end-of-life disposal of orbital components. Launch activities produce significant carbon emissions that could offset some environmental benefits of space-based power, requiring life cycle assessments comparing total environmental impacts with conventional energy alternatives. International environmental agreements may need updating to address the scale of proposed space-based power deployment. International development assistance programs could facilitate space-based power deployment in developing countries lacking adequate terrestrial renewable energy resources. Multilateral development banks and climate finance mechanisms might provide funding support for space-based power projects that advance sustainable development goals while demonstrating commercial viability. Such programs could accelerate global deployment while ensuring equitable access to space-based energy benefits. Standardization efforts require coordination among multiple international organizations, including the International Organization for Standardization, the International Electrotechnical Commission, and space agencies worldwide. Common technical standards for power transmission frequencies, safety protocols, and interconnection requirements will be essential for international deployment and interoperability between systems developed by different countries or companies. Public acceptance and engagement strategies must address legitimate concerns about microwave transmission safety, space militarization, and equitable access to space-based energy resources. Educational programs highlighting safety measures and environmental benefits could build public support for space-based power development. Transparent governance processes involving multiple stakeholders will be crucial for maintaining public confidence in these large-scale infrastructure projects. Economic incentive structures, including feed-in tariffs, renewable energy certificates, and carbon credit systems, may require adaptation to accommodate space-based power sources. Existing renewable energy support mechanisms focus primarily on terrestrial technologies, and may not appropriately value the unique benefits of space-based systems, such as continuous power availability and location independence. These implementation challenges require coordinated action across technical, regulatory, and policy domains, but successful resolution could unlock transformative benefits for global energy systems and environmental protection. The successful implementation of space-based solar power systems could fundamentally transform human civilization's relationship with energy, realizing Tesla's vision of abundant, wireless power transmission on a global scale. Unlike Tesla's terrestrial approach, orbital power stations could provide continuous clean energy to any location on Earth's surface, potentially ending energy poverty and enabling sustainable development in the most remote regions of our planet. Environmental implications of space-based solar power extend far beyond simple carbon emission reductions. Traditional renewable energy systems require significant land use that can impact ecosystems and compete with agriculture or conservation needs. Solar farms covering thousands of square miles, wind turbines across scenic landscapes, and hydroelectric dams flooding river valleys all represent environmental trade-offs. Space-based systems eliminate these terrestrial impacts while providing equivalent or greater energy output, preserving Earth's surface for natural ecosystems and human habitation. The scale of potential environmental benefits becomes apparent when considering global energy consumption patterns. Humanity currently consumes approximately 160,000 terawatt-hours of energy annually, with over 80% derived from fossil fuels. A fully deployed space-based solar power system could potentially provide clean energy equivalent to shutting down thousands of coal-fired power plants worldwide, dramatically reducing atmospheric carbon dioxide concentrations and helping stabilize Earth's climate. Geopolitical implications of space-based solar power could reshape international relations and economic power structures. Countries with advanced space capabilities might achieve energy independence while becoming major power exporters to nations lacking such technologies. Traditional oil and gas producing nations could face declining influence as space-based power reduces global fossil fuel demand. International cooperation in space-based power development could foster peaceful collaboration, but competition for orbital resources and technology advantages might also create new sources of conflict. Space-based power systems could catalyze broader space economy development by providing abundant energy for space-based manufacturing, asteroid mining, and human settlement beyond Earth. Manufacturing facilities powered by orbital solar arrays could produce materials and products impossible to create in Earth's gravity and atmosphere. Solar power satellites could support lunar bases, Mars colonies, and other ambitious space exploration projects by providing reliable energy infrastructure independent of local resources. The wireless power transmission capabilities demonstrated by space-based systems could enable new applications beyond large-scale electricity generation. Smaller satellites could provide power to remote sensors, emergency communications equipment, or scientific instruments in locations where traditional power sources are impractical. Electric aircraft could potentially receive power during flight from orbital sources, enabling new transportation capabilities and reducing aviation's environmental impact. Economic transformations resulting from abundant, low-cost space-based power could revolutionize manufacturing processes, enable new technologies, and reshape global trade patterns. Energy-intensive industries like aluminum smelting, steel production, and chemical manufacturing could relocate to take advantage of cheap, clean power, potentially reversing decades of industrial migration driven by energy costs. New technologies requiring substantial energy inputs, such as large-scale atmospheric carbon capture or seawater desalination, could become economically viable. Technological spillovers from space-based power development could accelerate progress in multiple fields including materials science, robotics, artificial intelligence, and wireless communications. Advanced solar panel materials developed for space applications often find terrestrial uses, while robotic assembly techniques pioneered for orbital construction could revolutionize manufacturing on Earth. Wireless power transmission technology could enable new consumer applications from electric vehicle charging to powering electronic devices without batteries. The timeline for achieving Tesla's wireless power vision through space-based systems spans multiple decades, but intermediate milestones could provide substantial benefits long before full implementation. Demonstration systems planned for the late 2020s will validate key technologies and build confidence for larger investments. Commercial systems beginning operation in the 2030s could provide clean power to specific markets while proving economic viability. Large-scale deployment throughout the 2040s and 2050s could eventually provide a substantial portion of global electricity needs. Educational and inspirational impacts of space-based solar power development could motivate new generations of engineers, scientists, and entrepreneurs to pursue ambitious technological challenges. Like the Apollo program's influence on STEM education during the 1960s and 70s, space-based power development could inspire students worldwide to pursue careers in science and engineering, creating human capital necessary for continued technological advancement. The journey from Tesla's experimental tower in Colorado Springs to orbital power stations beaming energy across the cosmos represents humanity's persistent drive to harness nature's fundamental forces for the betterment of all life on Earth. Success in this endeavor would vindicate Tesla's vision while opening new chapters in human technological achievement, environmental stewardship, and our species' expansion beyond our home planet into the broader universe.